the area will be. Who has not been to the board class? Maybe Ramon will give us the definite integral. Okay, thank you very much. Yes, that is the definite integral we want. No? We're moving from x equals 0 to x equals 2. Ceiling is x squared, floor is the x-axis. Okay, so A equals, can we continue this? X cubed over 3 from x equals 0 to x equals 2. So this is 2 cubed over 3, or well, we know that's going to be 0 anyway, so allow me to go directly to 8/3. Okay? Now, what if this is what we want? Can you give me the area class of this region? You have y equals x squared on one side, y equals 6 minus x on another side. So this region now will have two ceilings. If it has two ceilings, how many integrals are you going to need? Two integrals as well. Okay? I'll just clean up the board, and then I will ask for a volunteer to give me those integrals. Y equals x squared up to that tip. From that tip goes down via 6 minus x. Can you all see?
Yes.
I'll sketch it on the board. It's just like this, except that we have 6 minus x. Now, in many cases, class, if the sketch is given, if the functions are given, sometimes you are left to find the points of intersection. And you can easily do that if you have the functions anyway, right? For example, 2, 4, I already put that there. But this one, this point
6
is a point on the x-axis, which is also on that line. If it's on the x-axis, then y is always 0. So x must be 6. Okay, so that's 6. Why is it important to get that 6?
For the limits.
For the limit. It's going to be the upper limit of one integral. Okay. What is total area? Now we said earlier that there are going to be two integrals, right? Specifically what I mean here, class, is this. We already have that dividing line over there. We did not intend to put it, but we might as well use it. It was already there. No? That vertical line divides a region into two smaller regions, much like we had earlier. And the total area could be expressed by the area of this left-hand region plus the area of the right-hand triangular region. Right? So total area is area 1 plus area 2 as we had earlier, and therefore this would correspond to two definite integrals to be provided to us this morning by Cherry. Now whenever there's work being done on the board, always try to do it on your own, at your in your notes. Okay, so you can compare and you can check whether you're doing things correctly as well. Okay, thank you, Cherry. Anyway, I only asked for the integrals, right? So here are the integrals. First one is 0 to 2x squared dx, just like what we had earlier. And we know that the area is, I erased it, but you must have it in your notes. This is, okay, we solved this already, so we're allowed to do this shortcut. Okay. And this one, let's check. From 2, yes, left wall is 2, right hand wall is 6. Okay. Ceiling is 6 minus x, floor is the x-axis, so we just have that. Okay, now let's do the integration. Let's do this together, class. You have 6 minus x. Integration is linear, so you can just integrate one term at a time. Integral of 6, class?
6x.
6x. Integral of x?
X squared over 2.
X squared over 2. And you want to evaluate from x equals 2 to x equals 6. So you want 6 times 6 minus 6 squared over 2 minus 6 times 2 minus 2 squared over 2. Okay? We continue. We have 36 minus 36 over 2, 18. Now I'll get rid of the grouping symbol at the same time. This is minus 12. Minus minus gives us plus. 2 squared over 2, 2. Okay. 36 minus 18, 18. Minus 12, 6. Plus 2,
8.
okay. Are we done?
Yes.
Careful, that is the second area. Okay, that's the second area. Over here, don't forget we want to add 8 over 3 plus 8. Okay? Don't get caught in that trap. We're not yet done. 8 over 3 plus 8 gives us
32 over 3.
okay, 8 plus 24 over 3. Okay, that's total area. Okay. Any questions, class? It's easily done, right? It reflects what we said earlier. Area is additive. Even if you have irregular shapes, one irregular shape after the other, just add them all up. Okay? But here's another version of the additivity of area. What if we want instead something like this? You have y equals 2x as one ceiling. The floor is no longer the x-axis. I kept saying over and over again, I had a purpose in saying that, the floor had to be the x-axis. Because if the floor is the x-axis, what is the equation of the x-axis? Y equals? The x-axis has 0 equals y as its equation. Okay? This time, it has a different floor. If you look at this construction, you can see the walls right away, meaning the leftmost point, the leftmost x value is 0. The rightmost x value is, what is the rightmost x value? You look at the point of intersection. Point of intersection is indeed 2, 4. So you're going to end at 2. But what is the area expression? If you can do this, then we've had a great morning. We're done for the morning if you can do this. What do you think is going to happen? We're going to apply the additivity of area in another way. Now, if only the floor were the x-axis. If the floor were the x-axis, I'd have this. Would there be a problem? I can find the area because the ceiling is y equals 2x. The ceiling is 2x, the floor is the x-axis. So I just want the integral from 0 to 2 of 2x dx. No problem there, right? Now, if only the region were not this, but the region below. If it were the region below, why would that be better for us? If this were the region, why would this be better? Because the floor, again, is the x-axis, and the ceiling is just x squared. This is now the familiar formula for us. We're going to have 0 to 2 of the integral x squared dx. Correct? You can see that? Okay. So if it were the whole triangle, you'd have 2x dx. If it were this lower part, you'd have x squared dx. How do you use those two? Because those two we know how to find. To get this area, which as of this moment, we don't seem to know how to find. Okay? This is the pattern of solving things. Earlier, we did not know how to find the area of even such a region. We use rectangles. Now we know how to get the area of such a region. Now you're going to combine it with another irregular region. You get another irregular region. Both sides now, not straight, not circular, but you combine what is already familiar to get this next level of unfamiliarity. So what do? Opposite of adding? Yes, you subtract. No? So earlier, if we had that whole, if I could just reconstruct this again. If I have this triangular region, that's fine. I get just the lower sheet of paper, that's fine. Now how does it work? I get that triangular area. I remove the lower triangular area. I get the region I want. Right? How is that expressed? Using integrals. Let's see, who has not been to the board yet? Gerard. Okay. I'll just draw it here again. Okay. Try it, class. Okay, let's see. Area, according to Gerard, is going to be given by this definite integral. The walls go from 0 to 2. Indeed, from the left you have 0. To the right you have 2. Okay, that's going to come out as the abscissa of the point of intersection. The point of intersection, x squared and 2x are going to be the same if x equals 2. And the y value that will correspond to that 2 is 4. Okay. So the x values will go from 0 to 2. That's correct. And now what is the implication of this? 2x is the first ceiling. X squared is the second ceiling. Now what does it mean to have a 2x minus an x squared dx? Right? Now by the linearity of integrals, this is going to translate into what it amounts to, as we had demonstrated earlier using the sheets of paper, is this. We have this region, where if this is y equals 2x, area is the integral from 0 to 2 of 2x dx. Okay? And then we added a second one, y equals x squared. And if we're just going to get this region, say that is area 1, and this is area 2. Area 1 is the whole triangle. Second one, the area under a curve. Okay, under the curve, y equals x squared has the same lower and upper bounds. This now is x squared dx. Okay, this is under, that's a triangle, and this is under y equals x squared. Now, if we want this actual region, okay, the area of this region R, the area of the region R now, right, is given by the triangle minus A2. Okay, So if we do it one integral at a time, look at that. Okay, so from these two individual integrals, by linearity of integrals, these two we can combine into a single expression. So if I will continue over here, okay, we have the same boundaries, 0 to 2. Therefore, we can put these two into a single expression of this form. 2x minus x squared dx. We know how to integrate those two expressions. That's x squared minus x cubed over 3, evaluated from x equals 0 to x equals 2. Now, the second value being 0, we can do this in one step. Okay, we just evaluate at 2 because these two will just give us 0 when x is equal to 0. So we have 4 minus 8/3 or 4/3. Okay, good. Any questions this morning, class? You did it in one morning. It took them from the time of the Greeks to their time. Centuries, maybe even millennia. But you got it in one morning. Okay, you did very well this morning, class. Thank you.
Thank you, ma'am.